Now, how are we going to simplify some radicals that aren't perfect squares and we're not asked to approximate their value? Let's look at our first problem. Up here we're asked to find the square root of 13 to the fourth power, an awfully large number. Now remember, by definition, the square root of a number we're looking for is some number times itself to give us this number here. Now think back with your work with exponents. Would you agree with me here that I could rewrite 13 to the fourth power as 13 to the second times 13 to the second, or in other words, 13 to the second quantity squared? Think about that for a moment. This is under the square root sign. If you would agree with me that I could rewrite 13 to the fourth as 13 squared squared, remember the rule of exponents says when I raise to a power, I multiply. So this is really 13 to the 2 times 2, or 13 to the fourth power. Now why did I do that? Because I know that if I have any number squared, it can come out of that square root sign. So in other words, I can rewrite this expression simply as 13 to the second power, or if you know your multiplication tables, 13 squared is 169. Now again, what we did was we rewrote this 13 to the fourth as something squared. Once we get there, we're pretty much home free. Let's try our second example. A lot bigger, x to the 30th power. Now I know that when you see 30, you're thinking, that's not close to any perfect square I know. But remember, this 30 is in the exponent. So we're going to use our exponent rules. Now let's think a bit. Would you agree with me that I could rewrite x to the 30th power as x to the 15th times x to the 15th? Remember, when we multiply monomials, we add those exponents. 15 plus 15, 30. So just as in the previous example, I can rewrite this x to the 15th times x to the 15 as x to the 15th quantity squared. So if I put this expression in place of my x to the 30th, it looks like this. The square root of x to the 15th to the second power means I have two of these, and remember, whenever I have two of the same number, it comes out of the square root sign. So this becomes x to the 15th power. That's a bit confusing, so let's go through it one more time. What we do is we rewrite our square roots as something being squared. So here we have 13 to the fourth rewritten as 13 to the second squared, which we know is 13 to the second. That comes straight out, or in this case 169. Here we took a little bit more time because when you see the number 30, you're thinking that's not a square root, which you're absolutely correct. But because of our laws of exponents, we can rewrite this as x to the 15th times x to the 15th, x to the 15th quantity squared. I've got something squared under my radical sign, so I simply get x to the 15th power. The more you practice with these types of problems, the easier it will be. So let's try another one of these. Again, it just takes a little practice getting used to those exponents. Let's look at the following. Let's try to find the square root of 625 y to the fourth power. Now again, we have to try to think of a number times itself to give us 625. Now it may be a little work on your calculator, or you might have to do it by pencil, but 625 happens to be 25 times 25, or 25 squared. We just did the problem with, remember, 13 to the fourth power? So if 13 to the fourth power was a perfect square, then y to the fourth power should be a perfect square as well. In other words, we can write it as y to the second raised to the second power. Just check your exponents. When you raise to a power, You multiply. 2 times 2 gives us 4. Now that we have each of these quantities written as perfect squares, we know the square root symbol allows us to take them outside. So we're going to get 25 and our y squared. So that tells me then that the square root of 625 y to the 4th simplifies to 25y squared. I think we're getting the hang of it, but we might need just a little bit more practice with those variables. So let's try one more using some variables. Let's look at the square root of x to the 16th y to the 22nd. Now, what we're going to do here is what we did in that previous problem. Do you remember x to the 30th power we did just a few minutes ago? We have to ask ourselves, x to the 16th, is that a perfect square? Well, you're thinking, yeah, that happens to be 4 times 4. You're correct. 16 is a perfect square. But we're not looking for the square root of 16. We're looking for the square root of x to the 16th power. So don't be fooled. What we're going to have to do here is think this way. X to the 16th is x to the 8th times x to the 8th. Because remember, our exponent rules tell us that when you multiply these monomials, we add the exponents. 8 plus 8, 16. So what does that tell me? That tells me I can write x to the 16th as x to the 8th quantity squared. So let's do that. X to the 8th quantity squared. So be very careful as to the location of the numbers. When it's an exponent, we don't look at it as like the square root of 16. It's a square root of x to the 16th power there. Let's look at our second number, y to the 22nd. Now, obviously, 22 is not a square root, so you probably wouldn't make the same mistake you would have with the 16 there. Y to the 22nd happens to be a perfect square, believe it or not. It happens to be y to the 11th times y to the 11th. Because we know that 11 plus 11 is 22. So I'm going to rewrite my y to the 11th, my y to the 22nd as y to the 11th quantity squared. And again, whenever I have something squared, it can come out of my square root sign. So this gives me x to the 8th and y to the 11th. All right, now that I think we've understood, or we understand, how to work with our variables, let's go back to some numbers. But this time, our numbers are not going to be perfect squares. Let's ask ourselves how to find the square root of something like 98. Now you say to yourself, 98, kind of a big number. You're right. And you say 98, not a perfect square. You're right on that as well. But in order to simplify or find the square root of this number, we have to make sure that no factors of this number are perfect squares itself. Now, this is where that list of perfect squares will come in handy for you. You may not know this, and it may just take a little bit of practice, but 98 is a product of a perfect square and another number. In fact, 98 happens to be a product of 49 times 2. Now you say to yourself, why are you choosing 49? Well, the reason why I'm choosing 49 is because I know that 49 is a perfect square. I know that 49, the square root of 49 anyway, is 7. So what I'm going to do here to simplify this square root is I'm going to rewrite this square root of 49 as a product. I'm going to rewrite this as 49 times 2, but under here, 49 is 7 squared times 2. Now, since this is something being squared, it can come out of that square root sign. So it becomes 7 on the outside, 2, not a perfect square, so guess what? 2's just got to hang out on the inside of the radical sign. So the square root of 98 simplifies down to 7 times the square root of 2. These are probably the most difficult types of problems for most students, so don't feel too bad if you don't get it the first time. Just take a little practice. In fact, let's just try one more of these and see if we can get it. The square root, let's simplify the square root of 12. Now, the key to simplifying these not perfect squares here is to think of factors that are perfect squares. And you want to use the largest perfect square as possible. 12 isn't too bad, is it? Not that big of a number. In fact, what perfect square is a factor of 12? That's right, it's 4. So I'm going to say that 12 is 4 times 3. The reason why I choose 4 is because 4 is a perfect square. I rewrite this expression as 4 times 3, which I know 4 is 2 squared. So this becomes 2 squared times 3. Whenever I have some number squared under the radical sign, it comes outside the radical sign. So that leaves me 2 square root of 3. Now, these types of problems will take you a little bit of practice up front. What I would recommend is as you work through this, you keep your list of perfect squares nearby. Take one at a time, check to see if it's a factor of that number, break it into those factors, and simplify those radicals.